Section 3.2 deals with division, and I'm going to show a form of that called long division, in which, very similar to the way we did long division in elementary school, where we take one number into another, I'm going to show how you could do pretty much the same thing with one polynomial into another polynomial. Now, before I get into it, I do want to make one little comment, which is this is a little bit different than the way the book does it. The book calls it synthetic division, and what they do, as you can see an example here, is instead of writing out the polynomials, so here you have 3x cubed minus 2x squared plus 0x minus 150, and then you go through the process until you get a remainder at the end. They only use the coefficients that are in front of the polynomial terms. It works exactly the same way. I just prefer the more traditional form from the standpoint of it reminds you, it reinforces that you are dealing with these polynomials, where you can get a little bit lost when you're only dealing with the coefficients themselves. So it is a little bit different in the textbook. I don't have any problem if that's the way you'd like to do it. I just prefer a slightly different way of doing things. So, for example, let's suppose that we had x squared subtract 10x plus 9 divided by x minus 3. And so I'm going to set it up in a long division format. So here, inside the radical, if you will, x minus 3. And so the starting point is, basically what times x is going to give me an x squared? Well, x times x will give me the x squared. And so this is my first part, x times x, that's my x squared, x times the negative 3, that's my negative 3x. Then I will subtract. The x squareds are now gone, negative 10. And then when I subtract, of course, I'm subtracting a negative, so that becomes an add. Negative 10 plus 3x gives me negative 7x. I bring down the 9. And now, of course, negative 7 times x gives me negative 7x. Negative 7 times the negative 3 gives me plus 21. And then I subtract this part. Negative 7 subtract a negative 7, those go away. 9 subtract a 21 gives me the negative 12. And so that's my remainder because I don't have any x terms left. And so the answer then would be x minus 7 subtract 12 over x minus 3. This is the remainder part. And so I can write my original equation, which in this case was x squared minus 10x plus 9, as being the product of the divisor, what I was dividing by, and the quotient, and then here's my remainder part. Now, Rx is either 0 or with a degree less than gx. So here when I had the negative 12, there's no x term, so that's a degree less than what the divisor had there. If every degree from the largest to the smallest is not present, then we have to use zeros so that we fill it in. Now in this particular case, note we had x squared minus 10x plus 9, so every degree was there, the 2, the 1, and then the 0. But if something was missing, like for instance, let's suppose we had this right up, x cubed minus 10x plus 9, so there's no x squared term, I would need to put in a x squared term with a 0 in front because there isn't one, so 0 times that would nullify it. It does not really matter whether you call it plus or minus because of course it's 0, but I basically need to infill all the particular missing terms that might be true. If f of x is divided by an x minus k term, then the remainder is equal to f of k. If, on the other hand, f of k is 0, in other words, wherever we had an x, we plugged in k, if that is equal to 0, then we say that k is a 0 of the polynomial function. Real number zeros are the x values of the x-intercepts of the graph of the function. All right, so let's look at some examples now. And I'm going to blow it up just a little bit so it's easier to see. So, in this first case, we're going to do x plus 8 into x squared plus 13x plus 40. One of the things to point out as you're doing this is they can take a lot of space to do. It is really easier to do this on scratch paper, and then once you're happy with it, go ahead and transfer that to something else. All right, so again, the way I look at it is, I want to get rid of the x squared term, so something times x to give me x squared. Well, obviously that's going to be an x. So that'll give me x squared plus 8x. And again, all I've done is x times x for the x squared, x times the 8 for the 8x. Now, I am going to subtract that. So x squared subtract x squared, that'll be gone. The 13x subtract the 8x will give me 5x. Bring down the 40. So now I need a 5, because 5 times x will give me the 5x. 5 times the 8 will give me a 40. And again, I'm subtracting the whole line. And so 5x minus 5x is 0. 40 minus 40 is 0. And so my answer was just x plus 5. In this case, my remainder was 0. All right, let's look at the second one. I'm going to take x plus 3 into x cubed minus x squared, subtract 24x, subtract 19. So, first I want to get rid of the x cubed, so I'm going to need an x squared. So it'll give me x cubed plus 3x squared. Again, x cubed. X squared times x gives me x cubed. X squared times 3 gives me 3x squared. So I'm going to subtract that line now. The x cubeds are gone. I have x squared subtract 3 more x squared, so that's negative 4x squared. Bring down the 24x. And so now I want to match the x squared, and so I need a negative 4x. Because negative 4x times x will give me negative 4x squared. And then negative 4 times the 3 will give me negative 12. So negative 4x subtract a negative 4x, they're gone. 24 subtract a negative 12 will become negative 24 plus 12. So that will give me negative 12. And then I bring down the 19. And so now I want to get negative 12x with the x. So I need a negative 12. So that'll give me negative 12x. And then 12 times 3, that'll be negative 36. And again, I'm subtracting the entire line. So negative 12 basically plus the 12. They're gone. The negative 19 plus a 36 will give me a positive 17. Now this one, doesn't have any x term with it. It's just the constant 17. So I can not go any further. So this one's answer will be x squared minus 4x minus 12, and then plus a 17 over x plus 3. So I have a remainder this time. All right, now let's look at a situation in which not all the terms are there. We have an x to the 5th, then x cubed, so there's no x to the 4th. So we're going to need a 0 to take care of that, and then otherwise it's pretty much the same problem. So we're going to do x plus 8, and then we got to have x to the 5th minus 0, x to the 4th, or we could do plus, it doesn't matter because it's 0, minus 9x cubed minus 17x squared plus x subtract 15. So we're doing all of those terms. Well, first we want to get rid of the x to the 5th, so we need an x to the 4th. X to the 4th times x gives me x to the 5th. X to the 4th times the 8th gives me 8x to the 4th. I'm going to subtract both of those terms, so the x to the 5th, subtract the x to the 5th, that's gone. 0, subtract the 8, leaves me with a negative 8x to the 4th. Bring down the next one, 9x cubed. So now I'm going to need a negative 8x cubed, because the only thing it's missing is one x. So negative 8, that's the negative 8, and x cubed times an x, that's the x to the 4th. So negative 8x to the 4th. And then I got negative 8 times positive 8, so that's going to be negative 64x cubed. So this is what I'm subtracting this time. So again, those will be gone. I'm going to have negative 9 plus a 64, which will give me 55x cubed. Bring down the next one, which is the 17x squared. So now I'm going to need a plus 55x squared to get me 55x cubed. 55x squared times x gives me my 55x cubed. And then 55 times the 8 will give me 440x squared. So 55 subtract the 55, they're gone. 17 subtract the 440 leaves me with negative 457x squared. Now we'll bring down the x. So next I'm going to need a negative 457x. So that'll give me negative 457x squared. 457x times x. And then 457 times the 8, let's see, that'll give me a negative 3656x. And as you can see, it's very easy to kind of run out of paper. So it's really easier to do this on scratch paper first. The 457 x squareds are gone. I have an x plus the 3657. So that's going to give me basically 3657 7x, bring down the negative 15. And so the last part here I'll have is plus 3657. So that'll give me 3657x plus 2950. Let's see, that's plus. So plus 29,256. And so that's what I'm going to subtract now. That part will be gone, and I'll have negative 15, subtract another 29,000. So this last part will be negative 29,271. And so it'll be all of this, and then it'll still have this remainder. So the answer actually comes out to be x to the 4th minus 8x cubed plus 55x squared, subtract 457x plus 3657, and then subtract 29,271 all over the x plus 8. And so all of this is the answer to part C there. All right, number 2 says rewrite the answers in part 1 in the form of x minus k, that's the divisor, and then the quotient, and then a remainder if there is one. So the first one, there wasn't any remainder, so the f of x is just going to be x plus 8, and then the x plus 5. So that'll be the first one. That was how you would write this one in terms of, again, the divisor, the quotient, and then a remainder. There wasn't any remainder, so we don't have to worry about that. For part B, our f of x will equal the x plus 3 times the x squared minus 4x minus 12, and then plus the remainder 17 over x plus 3. And then for the last one, basically I'll write it here, f of x will equal x plus 8, then times all of that, and then there's the remainder part there at the end. All right. Number 3 here says use the remainder theorem to find f of k. So basically that means we're going to take and plug in k to our problem. So f of k will be f of 3 minus 2i, which means then we're going to do 3 minus 2i squared, subtract 3 minus 2i, and then plus 3. So everywhere we had an x, we put in the 3 minus 2i. Now, we have to FOIL this. That's going to give us 9, subtract 12i, plus 4i squared. And then here we have subtract 3, plus 2i, and then plus 3. Let's see. So remember that I squared is negative 1. So really, these guys are gone. Minus 3 plus 3. But we still have our 9. The 4i squared will become minus 4 because I squared is negative 1. And then I also have the negative 12i and the plus 2i. And so putting those things together, I'm left with 5, subtract 10i. So my f of k was 5 minus 10i. So basically what this is saying is if I had taken this and divided it similar to the way I was doing in the problems for number 1, I would have had this as my remainder, the 5 minus 10i. If this came out to be 0, then that would be a 0, but it would also mean that there was no remainder. So it's a little bit confusing because they call it the remainder theorem, but basically when I plug it in, if I have anything at the end, then I have a remainder. All right. For this last one, we want to determine whether k is a 0 of the polynomial function. If not, find the value of fk. And again, I'm going to pretty much do just what I did here. And if it comes out, when I plug it in, if it ends up simplifying to 0, then it was a 0. If it doesn't, then there was a remainder. So this case, here's the number I want to plug in. So f of k is going to equal f of negative 5, which is going to be negative 5 squared plus 4 times negative 5, subtract 5. So this is 25, subtract 20, subtract 5, which is 0. So k equal to negative 5 is a 0 of x squared plus 4x subtract 5. And that's the idea for determining whether k is a 0 or not.